Math can do a load of things. Most of the time we care about how it helps us describe, categorize, and even predict everyday reality. But there's more, much more. This is math. This is math. And this is math too. I didn't do anything fancy here, I just took some formulas and let the computer draw them. So, in this video, let me walk you through a few cool examples along with the principles behind them. We'll be working with pixel, fragment shaders, using ShaderToy. Let's start with something fun. Interestingly shaped surfaces, like this Batman logo. Normally, in math class, using pen and paper, we use explicit plotting. You pick an x, compute y is equal f for x, and put a dot or draw a line. But in a fragment shader, we flip that idea. Instead of drawing a line, we use implicit plotting. The shader runs for every single pixel on the screen at the same time. For each pixel at xy, we ask, is this pixel's y position below the top curve and above the bottom curve? If yes, color it. If not, leave it. To render the Batman symbol, we don't write one giant monster equation. We break it down into two main boundaries, a top and a bottom. And because the logo is perfectly symmetrical, we can cheat. We use absolute value. That means we only compute the right half. The left half mirrors. There's a helper function called getBottomTail. This handles that tiny inner curve near the bottom of the tail. Inside main image, every pixel gets mapped into a custom coordinate space from -8 to 8 horizontally and -5 to 5 vertically. The top half of the logo comes from 3 regions. For x, between 3 and 7, we draw the outer wings with a scaled circular arc. Between 1 and 3, we shape the shoulder using constants, linear terms, and a curve subtraction for that smooth slope. And for x less than 1, we build a head and ears, tapered lines for the ears, a rising slope under them, and a flat top. The bottom half has 2 main parts. For x between 4 and 7, we mirror the top wings downward. And when x is less than 4, we craft the inner wings and tail using a linear term, a curved tweak, a downward shift, and the tail function from earlier. Once we've computed the top and bottom boundaries, the shader simply checks whether each pixel lies inside the bat shape. Smooth step gives us nice anti-aliased edges, the background is kept dark, and the bat shows up in a bright emerald green. Here we have a shader that draws a Phyllotaxis spiral. This mathematical structure places each point at a golden angle from the previous one, and is the exact pattern we see in sunflower seeds, pine cones, and lots of plants. At the top, we define pi, the golden angle in radians, and how many points we want. There's also an HSL to RGB converter for coloring. Inside main image, we convert pixel coordinates into centered UV space. We track the closest spiral point to the current pixel, its distance, its hue, and its size. Then comes the core, a loop that generates all the spiral points. For each index, radius is square root of I. Angle is I times golden angle. That's it, that creates this iconic sunflower spiral. For every point, we compute how far it is from the current pixel. If it's the closest one, so far, we remember its hue and size. The hues cycle along the spectrum using a fractional multiplier. Afterward, we create a soft glow around the chosen point with smooth step. Convert the hue to RGB, apply the mask, and write the final color. The result? A beautiful glowing golden angle spiral. You might know the formula Z is equal to Z squared plus C. That's the Mandelbrot fractal, the legendary infinite pattern. In the shader, each pixel becomes a point C in the complex plane. We start with Z is equal to 0, then iterate Z is equal to Z squared plus C up to 100 times, or until Z exceeds 2, absolute value of Z. The number of iterations before it escapes becomes the pixel's color. We map that to a hue, convert to RGB, and keep the non-escaping points black. That gives us the classic Mandelbrot silhouette with smooth rainbow coloring. Next up, an animated plasma effect. Every pixel gets a normalized UV coordinate. We grab the time value and then blend 4 sine waves, one along x, one along y, one that mixes both, and one based on distance from the center for circular ripples. Adding these creates a dynamic plasma pattern. We map it to the hue, animate the lightness, convert to HSL to RGB, and write it out. The result is a smooth, colorful field with organic motion. Our last shader procedurally visualizes a structure inspired by the Clifford Attractor. Each pixel gets mapped into centered UV space. We define constants A, B, C, and D, which control the attractor's shape, how points twist and fold. We take the pixel's position, scale it outward, and iterate it through the attractor equations about 15 times. Each iteration applies sine and cosine transformations, creating structured chaos. Instead of simulating millions of points over time, we compute it directly per pixel. After the iterations, the color is determined by the final position, hue from sum of x plus y, saturation at full, and lightness based on distance from the origin. The result is a fractal-like pattern with depth and complexity. Across all these shaders, you might notice different approaches to UV coordinates. The Batman shader uses a custom domain from -8 to 8 and -5 to 5 for perfect proportion and symmetry. The Phyllotaxis Spiral centers the UV space and scales by vertical resolution, so the spiral radiates symmetrically. The Mandelbrot shader also centers and maintains aspect ratio, so the fractal fills the screen without distortion. The plasma shader works mostly in normalized 0 to 1 space, adjusting only the radial distance from central ripples. The Clifford Attractor uses center expanded coordinates to give the attractor room to unfold. Different UV strategies lead to completely different aesthetics, symmetry, and layout, one of the core tricks behind generative visuals. And that's it for today. Thanks so much for watching. If you enjoyed this and want to see more in the future, don't forget to hit the subscribe button. See you next time.